Oops, just a sec. Okay, so let me. Can you see my screen? Can you see my desktop? No.
Not yet.
Not yet. Okay. Yeah. Let's see. Why? Let me actually leave and come back. I think there is a little bit of an issue. You guys stay there. I'll be back in a sec. Okay. Okay. Let me share now. Okay, now I think I can share. Okay, so you can see my desktop, right? Yes?
Yes, sir.
Yes, sir.
So this is the Nobel Prize discovery announcement. So the half, so the 3 people got this prize. Half of the share goes to Roger Penrose for his theoretical studies and for the discovery that black hole formation is a robust prediction of the general theory of relativity. That's this gentleman here. And the other half is split between these 2 people, Reinhard Genzel and Andrea Ghez. And that's on the discovery of supermassive black hole at the center of our Milky Way galaxy. So the prize is on black holes. So this is on theoretical, the theoretical side of it, that black holes can form generically in general relativity, and this is on observational detection of supermassive black hole in Milky Way. So these are astrophysics. These are on astrophysics. So let me actually show. This is actually the second half of the Nobel Prize, for which the observational detection of supermassive black hole in the Milky Way, in the center of the Milky Way. This is actually really, really cool. What you are seeing here. So this is the location of the supermassive black hole. Can you see my arrow?
Yes, sir.
So this is
Yes, sir.
Good. So this is the location of the galactic center black hole in white star. Okay, and what these dots here that you see are actually stars which are moving around this supermassive black hole because of the gravity of this supermassive black hole. So basically these are Keplerian orbits. So this is infrared observations from the Keck telescope in Hawaii, and this is from the UCLA group. So from Andrea Gez's group, they have very nice movies on their webpage. So let me play it. What it will show is the location of these stars as they move over a period of like tens of years. Okay, and this thing at top is the year. So this snapshot is in 1995, and this is the scale. So this is 0.24 arc second. So this is a very, very tiny angular scale. So you're looking in a very small region around the galactic center. So let me just play the movie. So what you see are these stars are like test particles orbiting around a massive object, which is this dark supermassive black hole. Let me just play it so you can see 1999, 2000. So it will run over it. So you saw this blue, yellow one. This star, this is a very elliptical orbit, right? So this is at the focus. In fact, this green is even more elliptical orbit. So when and the source of the mass is at the focus. So you can see this is a very eccentric orbit, and the object moves very quickly close to the object, which is Sagittarius A star in this case. So these are essentially Keplerian orbits, and the achievement of these people, the the group of Reinhard Genzel and of Andrea Ghez, is to map these out very carefully, because this is, this kind of nice animation can only be made if you're able to have very high resolution viewing of the galactic center region, which is extremely crowded. So, this is actually extremely simple to explain. These are just Keplerian orbits of stars around a dark object, which is supposedly the supermassive black hole in the center of our galaxy. And the point is that, for example, this green trajectory went so close to this massive dark object that it can be nothing but a very compact object, and the only possibility seems like it's a supermassive black hole. So by measuring the time period, of these orbits, you can actually get the mass of this. This is just Keplerian dynamics, a two-body, in fact, not just two-body, but this is a very massive body, like 4 times 10 to the 6 solar mass compared to like 10 solar mass of this. So this is like a textbook one-body problem with general electricity. So this was the second part of the discovery, and the first part was, of course, the theoretical elucidation of existence of black holes. Anyway, I thought it would be cool to talk about this since this was announced yesterday. Okay, so now we'll come back to our class. You can see my slides now. Hello.
Yes, sir.
Yes, sir.
Any question on that? The visual that I showed.
Sir, the supermassive black hole they are saying, but if you study the formation of black hole in through general relativity, there you can conclude that you can't detect the black hole horizon. I mean, that will be the future infinity. So how they are conclude?
This is not event horizon. This is not at the scale of the event horizons. This is at about like a much larger scale. But still, that this star is actually grazing very, very close to this dark object, right? And this is like of the order of 1000 AU or something like that. And that's very, very small. You don't have anything else. So it has not hit some surface or something. So this is not a star which has a surface. If it had hit some surface, there would have been an explosion, something. But it just goes as if it's just orbiting around some invisible thing. And the most likely explanation for this is black hole, supermassive black hole. Now, last year, they have imaged the supermassive black hole in M87, which is a nearby galaxy.
Yes.
So this is sort of
Yes.
along the line. This is the same line of research, and a lot of same scientists are involved in that. That's called the Event Horizon Telescope. That's like on the scale of the event horizon of the black hole. This is much larger scale, like 1,000 times larger, 100 to 1,000 times larger. So these stars are not moving at sea, right? If they are close to the event horizon, they would be moving at sea. These are moving at 0.1 C. So they are like 100 times farther from the event horizon. So like this green guy, when it was close here, it was at 0.1 C, which is actually very fast. Stars are massive objects. To accelerate it to 0.1 C is no small thing. Okay, so good.
Yes.
Any other question?
Sir, how did they find the where exactly this star was located from, from the focus of the ellipse,
See, they just observe these orbits, right? And then they fit a Keplerian orbit to all these stars. And the good thing is all of them give the same location. So you have like orientation of this orbit. So you have a lot of parameters, but you also have a lot of data points. All these are independent. The motion of all these stars is an independent way of finding the location of the central dark object. And the good thing is all of them give the same location, and the same mass. So this is very, very unambiguous. There is no doubt about there being a dark object. Whether this is a black hole or not, it's not entirely sure. You can have very dense, like a neutron, you can have a 10 to the 6 solar mass neutron star, but those things are not stable, right? We know it's not possible to create those things from any mechanism. So, I mean, even this left very little doubt, but then this Event Horizon Telescope has imaged regions around supermassive black holes. So that's even tighter observational evidence. Anyway, any other question? There will be some, there will be talk in the department about this anyway in future. But I thought since this was yesterday's news, I will share it. No more questions? Then we can move on to the class. Okay. So, I'm not sure, but there are things called magnitudes. In astronomy, for historical reasons, we have units called magnitudes, right, which are used to quantify the flux and the luminosity. So let me first tell you what is a flux, right? So the sun has a luminosity of 4 times 10 to the 33 erg per second. So that much energy comes out of the sun per unit time, and it goes in all directions, right? So that's the luminosity. So luminosity is an intrinsic property of an object, okay? But at Earth, we are measuring some energy that comes out from the sun, and we use something called a flux, which is energy per unit. Energy per unit area per unit time received at the location of the Earth. That's the flux. So flux changes if you move away or closer to the sun, right? So flux is not an intrinsic property of the sun, but it also depends on the location of the observer. So for every object, you have a luminosity, and when we observe this object from the Earth, we are measuring its flux. Okay, so these are really fundamental and very basic properties of astrophysical observations. So flux is energy received per unit area per unit time from some object, and luminosity is just total energy emitted by that object. I mean, this I'm sure everyone knows it. Any doubt on this? Any question on this? Okay, I guess not, right? Which is good. So, but the funny thing is these magnitude system for quantifying these fluxes. So magnitudes are logarithmic units for both luminosity and for the flux. So the intrinsic brightness of the object, which is luminosity, and the flux, which is measured at some distance from the emitting object. So these are logarithmic units, and these are like decibels for sound, right? When you have sound energy, you use decibels, which is also a logarithmic unit. So the intensity of the sound, you do a log of that, and then that's how you get the decibels. In the same way, magnitudes are logarithmic units for luminosity or flux. Okay, and for both of these there are historical reasons, because our ears and our eyes are sensitive to a huge range of intensities, right? And if you have a huge range of things that you can measure, you don't want to deal with like 10 to the 10, 10 to the 20, 5, and so on. It's useful to take logarithm of that, and then you get like more reasonable numbers to deal with. So this is the historical reason for the existence of the magnitude system. Okay, and small m is the symbol used for apparent magnitude. Apparent magnitude means flux. So small m is quantifying the flux, which depends on how far the body is, and absolute magnitude, the capital M, is the luminosity equivalent of luminosity. So this is the definition of magnitude. This is apparent magnitude. Small m equals 2.5 log to the base 10 flux plus a constant. So basically this is a logarithmic unit. This is what it says, right? If you want to get a magnitude, you just take a log of flux and multiply it by 2.5 and add a constant. So this is the flux unit. So as I said, if you go far away or closer to the sun, flux is different. So similarly, the apparent magnitude depends on the distance of the object you are observing. Okay. Now this one, capital M, is the is called absolute magnitude, right? And absolute magnitude is equal to the apparent magnitude if you place the object at 10 parsec. So this is the definition of, this is sort of like fixing this constant, right? So if you place the object at 10 parsec, that's the two become equal, the apparent magnitude and the absolute magnitude. And you can see that apparent magnitude has become fixed in this case because you're putting it at a fixed distance, right? So then it is equivalent to luminosity, which is capital M. So for reference, for the sun, the absolute magnitude is minus 26.74. Sorry, I have actually missed a negative sign here. There should be a minus 2.5.
Yeah, I mean, I was also.
Yes, you have got it right. So there's a negative sign which I have missed. I'm sorry about that. Yes, so that's why you see the sun is the brightest object. So it has a very big negative value as an apparent magnitude, right? But its absolute magnitude is plus 4.83. And we know that sun is an ordinary star. It's not particularly bright. So if you place everything at 10 parsec, the sun will not stand out. The sun stands out because it is so close. It is much lesser than 10 parsec, right? This is at an astronomical unit. Anyway, so this is like a small primer on magnitudes. Don't be afraid of it. A lot of things in astronomy is because of tradition. It's not something that astrophysicists use or love to use now, but since astronomy is such a old science, you're stuck with a lot of such traditional things, and you don't want to miss out on all the fun just because there's a little inconvenient convention around. Okay, so just be careful about this negative sign. That's it. Okay. Okay, so as I said, the other thing is that it's useful to know some numbers in astronomy. Of course, you can always Google and find what is the distance of the sun from the earth and so on. But it's a good idea to know these. Like 1 AU is 1.5 times 10 to the 13 centimeters. And you may have noticed that I'm using units like centimeters and ergs. So in astronomy, we use CGS units. So a lot of electromagnetism becomes very easy if you use CGS units because you don't have those 4 pi epsilon naughts and mu naughts hanging around. Okay, so CGS units have their own advantages. So so a lot of you may already know that the stars are very close to black bodies. So whereas there are things called active galactic nuclei or accreting black holes, which have a very broadband spectrum. So black holes emit, the material around black hole emits radiation in a huge range. So going from radio, so this is radio frequency, 10 to the 10 hertz or 3 centimeter to as high as MEV or even GeV or TeV photons coming out from these objects. So you have you need to have coverage in all the wave bands to understand these objects very well. So I'm actually not going to talk about all this, but this is just to show that there's a huge range of frequencies covered in the astronomical observations, and we will actually talk about a lot of mechanisms which emit in different wave bands, right? The stars generally emit in optical, infrared and UV, and they're essentially black bodies, so they are much easier than these more complicated sources. Similarly, we will be looking at objects which are far away. So there is something called Hubble expansion, right? So this is more like an advertisement of this course. This is really not the beginning. So I'm not going to this is just sort of giving you a sampling of what are the different observations that we do with the photons that come to us. So photons, we have observed the universe with photons for a long, for thousands of years, right? Ancient people looked at the skies, and then they were very familiar with constellations and whatnot. So we have used photons for a long time. And 100 years ago, we were just limited to optical photons because our eyes are sensitive to optical photons. But later on, this window was expanded, from radio all the way to gamma rays. Okay, so for example here, so you must have also learned about or heard about Hubble expansion. So if you go far away from the Milky Way, you observe that the galaxies which are farther away from us are moving faster away from us. So this is the Hubble expansion. This is sort of the basis of the Big Bang origin of the universe, right? So, and this is not just some science fiction or something. We have observations to tell, which sort of confirm to this. There is cosmic microwave background, which is also millimeter photons coming from really very early time in the universe. So what I am showing here are something called spectra, or the energy distribution of photons coming from objects called quasars. So the point of showing this is that we have these objects like stars and AGN, and they have a lot of unifying features. The energy emitted by them at a given frequency is very similar. Right? For example, you have this, and this as the spectrum. For quasars at different distances from the Earth, these are the redshifts. So you see that there's like a characteristic peak. Right? So this is the peak of quasar at 6.3. This is the peak for redshift 4.4, and this is for 2.8. The main difference between these quasars are that they are at different distances from us. So these lines, these characteristic lines that come from these atomic transitions are shifted to different wavelengths, right? So this is redshift. So what is meant by redshift? If you observe some particular line that for example, Lyman alpha line, for example, n equals 2 to 1 transition of hydrogen, that has a wavelength of 1216 angstrom. Okay, but if you put this object at very high redshifts, the wavelength of the photon that you receive here on Earth, it goes towards red. You see, the farther you go in redshift, this moves to redder and redder, or the longer wavelength, right? On x-axis, as you increase, as you go towards the right on x-axis, this is longer wavelength, right? So this is in fact, this is the definition of redshift of an object. The redshift is the ratio of the observed wavelength divided by the emitted wavelength, which we know, right? We know atomic physics, so we know the lab frame wavelength of various important transitions. So we know the redshift of a lot of these objects because we know these characteristic features in their spectra. So just by looking at this peak, we know that this object is at redshift of 6. Once we know that, when the objects are not very far away from us, redshift can be approximated as V by C. So V is the speed at which the galaxy is receding away from us. If the galaxy is moving away from us, this is a redshift, right? So this is all like behind this Hubble expansion. Anyway, this is, as I said, this is a primer of this course. These are just 3-4 examples that I could just gather. Yes.
Sir, in this equation, we have one known, that is lambda observed, and lambda emitted we don't know, but
we know this. this. We also know lambda emitted because we know a lot of common lines from atomic physics done in the lab, right? We have spectroscopy as a science has been around with us for 200 years, right? So we know that there are these Balmer lines, Paschen lines, for common elements. Hydrogen is the most abundant element in the universe. So for common element, we know a lot of these transitions. So this actually, in some sense, is known. This is also known. This is what you measure. So for example, in case of stars, right? You see these are stellar spectra, and you see that, for example, look at this F star or a G star. You see these absorption features, right? So this is H alpha, H beta, H gamma. So these are transitions. So H alpha is transition from n equals 3 to 2, right? This is a Balmer line. Alpha transition of Balmer from n equals 3 to 2. This is n equals 4 to 2, 5 to 2. You see all these features line up exactly where they should line up according to atomic physics, right? So we know a lot of these things. So in these spectra, we know we can actually identify. So if this is a quasar at some redshift, this bump, we know exactly where this bump should occur in wavelength. We know a lot of these absorption features in these spectra too. So we have a very good sense of this. If you have multiple absorption features or emission features, we have a very good sense of this. We observe this, and by this we just get the redshift. Does it make sense?
Sir, what is the main line? Is it H1 alpha?
What is that?
What is the main peak? I mean, every picture has a main peak, right? Before it.
Right. So
The
H is this
quasar.
n equals 3 to 2 transition of hydrogen, right? This is the simplest model that we do, right? This 13.6 eV 1 by n square minus 1 by n2 square, right? That's the energy emitted by transition from level n1 to n2, right? If you have a hydrogen atom, a neutral hydrogen atom, and if you have an electron which is excited, which goes from n1, n2 to n1, it will emit a photon, right? And these lines have very specific frequencies or wavelengths, right? So H alpha transition is n equals 3 to 2 transition of hydrogen, neutral hydrogen, right? Excited state n equals 3 to n equals 2 gives rise to this photon, which is at 6,600 angstrom.
So the main peak that we know.
Which main peak?
The next slide. The next slide.
Oh, the next slide. This one. Oh, yeah, this one. Yeah. So these are from quasars, and we know that the quasars have a very prominent Lyman alpha n equals 2 to n equals 1 transition. Yeah. This corresponds to n equals 2 to 1 transition.
Okay.
Right. And everything on this side, you will actually notice one thing. The higher the redshift is, the spectrum on the low wavelength side, smaller wavelength side, has less energy coming out. Right, 6.3. There's almost nothing, no photons coming out at less than this wavelength, and so on. So this is all. This is a huge area, and this basically has to do with the fact that the universe is fully ionized up to redshift of 6, but beyond that it becomes more and more neutral. So all these photons which are coming on the left side of this have energies which are larger than the n equals 2 to 1 transition. So all these photons which are intrinsically there are absorbed on the way, because there is a lot of neutral hydrogen, and that absorbs all this, and all this emission does not come to us. Okay, but anyway, let me not get lost into all these details. This is just to sort of give you a primer of what are the different things that photons are used by astronomers. And it's a very so So this is sort of astronomy done with photons. You know, even within that, in the astronomy done with photons, optical, infrared, UV, and a little bit of UV is the most sophisticated, because these are the things that we have been around for a long, long time. There's huge development in X-rays, gamma rays, so on, but they are still not as sophisticated as optical. So a lot of astronomy is optical astronomy, and in fact, there are new messengers now. You know, you all have heard about gravitational wave detections. So neutrinos. These are the ways in which we learn more information, but not through photons, but through other messengers like neutrinos and gravitational waves. But all this is very, very recent compared to the observations of photons, especially optical photons that have been around for thousands of years. Okay, so maybe so do you guys know about gravitational waves and neutrinos?
Sir,
right?
I have a question. Sir, this
Yes.
is Ritesh.
Who is this?
I have a question.
Yes.
Ritesh. So
Yes.
can you go back to the previous slide?
Oh, yes.
So here the cosmological redshift, and
Yes.
so this is due to the expansion of the space between the galaxies, or is this because of the velocity itself of like different galaxies?
Right.
This
So you know, the galaxies at largest scales, you can actually think of them as they're embedded in this space which is expanding. That's the easiest way of interpreting this. Okay. So
yeah.
the nearby objects can have peculiar velocity. They can fall. So for example, you know, Andromeda galaxy is coming towards the Milky Way galaxy, but that's like the local neighborhood. At large scales, everything is moving away from everything else in the universe. But you have to go beyond tens of megaparsec for that. Okay.
Okay.
So you know that. Yeah, let's not.
But my question is actually, so this cosmological redshift and the redshift due to Doppler effect, so are they like exactly same, or is there any fundamental difference between them?
Oh, see, cosmological redshift is big. You know, I mean, cosmological redshift means that the universe is expanding. Okay, but the way it manifests in observations is through Doppler shift, right?
Okay.
They're
Yeah.
very, very closely related. For example, if you have like an object which is moving away from us or towards us, it can also have a redshift just by this
Yeah.
definition, right? But this will be
Mhm.
totally due to motion, Doppler, right? But we don't interpret it as cosmological redshift, right?
Yeah.
So redshift is a generally defined quantity, which is just this, observed wavelength divided by emitted minus 1. And that you can define even for an object which is moving away or close to us, has nothing to do with cosmology. But
Yeah. Yeah.
is at a cosmological distance, this redshift is a cosmological redshift. That's the difference, okay?
Okay.
Okay, so when generally the large redshifts are cosmological redshift, you know, redshift 0.1 or larger are generally cosmological because 0.1 redshift means that velocity is 0.1 c. It's very difficult for astronomical objects to move at 0.1 c. Although at the beginning of the class I showed you a star which moved at 0.1 c. That's rare, and it's rare because only near a black hole or something like that you see that. So redshift greater than 0.1 or 0.05 or 0.01 is very likely to be cosmological. The other possibility is relativistic beaming. So if you have a jet coming towards you, that can give you, but that's not for common objects. Anyway, so now is where I actually start the course. So these are the different units that we use to quantify the photons, right? So we can sort of say wavelength, like we can say centimeter wavelength astronomy, X-ray astronomy. So these are the different wavebands, and there are no hard and fast boundaries between them. They are sort of commonly used. So you can talk in terms of wavelengths or frequency or energy in EV or in terms of temperature. and they're all related, right? So we know that for a photon of energy E is equal to h nu, and you can actually get a temperature for energy by just using E equals kT, right? K is the Boltzmann constant. Similarly, if you know the wavelength, you can get the frequency. All this is very, very basic stuff. I am sure that everyone knows this. Energy is just h nu, and so this c is the universal speed of light, kb is the Boltzmann constant, h is Planck's constant, and this is also useful to remember. 1 eV is 10 to the 4 Kelvin. Okay, as I mentioned previously, it's useful to memorize some of these very, very basic numbers, and it's not very hard, and it actually makes you can actually calculate something very quickly, and that gives you a lot of intuition, right? For example, we memorize how many meters are there in a kilometer, right? We don't have to, we can always Google it up, but our mind works better when we know these facts, and we can imagine that the distance from home to school is in a few kilometers, right? So in the same way, knowing some of these numbers by heart gives you a lot of intuition. As you have noticed, we're using CGS units, and CGS units for charge and voltage are a little tricky, right? 1 coulomb is 10 to the there is a coulomb that we use in SI units, but in CGS we have ESU and stat volt and so on. So you just have to be careful about this, and there are no those 1 by 4 pi epsilon naughts, which are really annoying in SI units, are not here in CGS. So it will take a little getting used to the CGS units, but they'll be very, very useful, especially for ENM, right? For mechanics, it doesn't really matter. 3 times 10 to the 10 centimeter per second or 3 times 10 to the 8 meter per second, not much difference. But here is where CGS units will be much more convenient. It again, just for intuition, you have to have like a sense of these numbers. For example, centimeter wavelength, 21 centimeter line. There is this very famous transition, hyperfine transition of neutral hydrogen, which occurs at 21 centimeters. So 21 centimeter this is a logarithmic scale. So this is about here. So this is 10 centimeter, 21 centimeter. That's radio, right? CMB, microwave, millimeter microwave, cosmic microwave background peaks here. Stars emit in optical and UV and infrared, right? So black holes emit a lot of times in X-rays and even gamma rays if you're looking at the jet. So, again, this is no rocket science. This is very simple stuff. But, knowing these numbers, having a feel for these numbers give you a lot of intuition, okay? For example, optical observations are at 10 to the 14 hertz. Radio 100 megahertz to gigahertz, 10 gigahertz. GMRT operates at hundreds of megahertz. People like in X-rays and in gamma rays, people use EV because that's more natural in that. So you have 1 keV. This is sort of like an X-ray photon. Or a MEV is like a gamma ray photon. Have a little feel for this. X-ray, the thermal temperature for X-rays is around 10 to the 7, 10 to the 8 Kelvin. Okay. So this is it for the, this is really the primer for this course. And now is when I have about 15 minutes. Now is where I am actually going to sort of. So what I was thinking is when I actually have to write things, I will use on this general, you can see my screen, right? On this general channel, there is something called this class notebook. You can see my screen, right?
Yes, sir.
Okay,
Yes,
so this class notebook is something where I sort of figured out that, I can put my notes, and a lot of students can submit their, for example, if we give you exams, you can submit your exam, you can scan your exam thing and submit here. So this is actually very useful. It's at the same place. So oh, sorry, content library. So content library is where I will I will be okay. So this is where I'm actually this is where my slides are, and this is where most of the stuff that I do will be. Okay, I have never tried it before in a class. I just sort of tried things on my own. So this is where I can even scribble and write here. Okay, but before I do that, are there any questions on the material that I? So again, till now I was actually just sort of talking about very general stuff, which are more like why should you care about this course. Now is when I'll sort of slowly start with the actual material. Okay, so any questions on what I presented till now? No, then we can actually slowly start with the main content. Okay, so here I have tried it. Let's see. Hopefully this will work. Okay. Okay. So again, I actually mentioned this concept of. Oops. Oops. Why am I not able to? No, just a sec. Little technical problem. I have this pad on which I write, and I tried it. It was working. Let me try again. Oh, sure. Just a second. Okay, I can write with my mouse. I was hoping that I can also. No, sure, man, this is not good. Okay, give me a second. Let me. Sorry about that. I just stopped feeling it. Yeah, we have to figure this out because most of the class will actually have notes. I will not just be doing I will not just be doing presentations. There will be no. Okay, so let me. This is embarrassing.
Sir, I think there is a text window on the left side. That's why you are not being able, I think.
No, it's not because of the C. I can actually write here with my mouse. It is something to do with the setting of this pad, which I actually used it. But anyway, let me use the mouse for now. Okay, since there's only not a lot of time remaining, I don't want to waste all that time. So the first concept that we will be so the first concept that when we start this course we'll be doing is the concept of flux, right, and luminosity, as I said. So if you consider some small area, right, dA, right, so this area is a small area. It has some normal direction and hat, right? So what is flux? So flux. So flux is defined such that if you have such an area, so dE, right? So dE is the amount of energy carried by photons through this area, okay, and this is given by flux times this area times the time dt. So how much energy crosses this area in all directions? So you have to consider photons going in all directions. How much energy crosses this area so this is the energy. So the bigger the area is, the more the energy will cross. The longer you wait, the more the energy will cross. So flux is the energy crossing an area per unit area per unit time. Okay, so basically flux is net energy. You can see what I'm writing. Crossing.
Yes.
Per unit area. I'm using mouse actually. I was hoping to use the pad, but that's fine. So this is the definition of flux. So you will have photons. So this sort of area is already fixed. So you will have photons going in all directions through this small area, right? You will have photons, going in, out, in all the possible directions. So you will have photons going in all solid angles, right? All of you know about solid angle, right? So you have, photons going in all possible directions. So the net flux, so if you have like a isotropic source of radiation where photons go in all directions, there will be no net crossing of photons in positive or negative direction, right? So flux also have a sign. So once you have an area, so you fix an area, and then the question you ask is how much flux of radiation or photons crosses this area per unit time and per unit area. Okay. So if you have radiation which is pointed perpendicular, or your area is perpendicular to this direction of photons, this does not this is like an area which is in the plane of these rays, so there is no energy crossing this area. So in fact the energy crossing is actually equal to flux. So energy crossing is zero in this case. So the flux, in fact, sorry, just a second. So the flux in this case is actually zero. Flux crossing this area is zero because the photons are not crossing this area. They are just sort of moving past it. Now let's just consider, just sort of clarify this concept a little further. So suppose you have photons, you just have these two beams of photons, and photons are only traveling in these two directions, right? So these are the beams of photons. Now, and if the intensities are equal, how much is the flux through any area? Right, if you consider any area here, the equal number of photons crossing this and this in the two directions, so flux is zero. So this is not isotropic emission, right? Isotropic emission would be rays coming in all directions. Okay, so the important concept here is that direction is important. Okay. So in this case, it's clear, right? If the area is like normal or whatever the direction you choose for the area, since the equal number cross in opposite directions, there is no net energy crossing this area. So flux is 0 in this case for all possible orientation of surfaces. Because, you know, it's sort of like addition of these two vectors add up to 0. So whatever component you take of the vector, it's 0. Okay. Now, suppose again you have this, right? So this is, say, the direction of incident photons. Okay. And you have an area which is sort of, let's call this area has a direction n hat, and the direction of the photon is this. Let's call it omega hat. The omega is this solid angle. So the photons are moving in various directions, and the photon direction is denoted by this omega hat, and this is angle theta, let's say. Okay, so in this case, flux through this area which is at angle theta to the direction of the beam is proportional to cos theta, right? Simple. And the flux includes all the possible directions of the photons. Now, the sunlight, right? The sunlight that we receive on Earth, what do you think is, so this is actually a question to the class. What do you think is the direction of the photons that are coming from the sun? And, we are sitting in our rooms, the photons that we get, what is the direction of those photons? Are they sort of like beamed, or are they coming in all directions? Or it's a question, please.
They are beamed.
Anyone?
They are mostly beamed.
They are mostly beamed. If they were mostly beamed, then if you look away from the sun, you should see darkness, right? If the Earth did not have an atmosphere, that would be the case, right? You must have all read about Rayleigh scattering, right? So the molecules in the atmosphere, they scatter radiation, and that's why it's so pleasant to be outside. Otherwise, there would be darkness, and if you're not looking directly at the sun. Of course, you're right that there is a little bit of anisotropy, that if you look directly at the sun, you receive more light. But there's, most of the radiation that we are used to is the scattered radiation. Okay. So if you are say in a room, so you're sort of shaded by the direct sunlight, but you still have pretty brightly lit room. So it's sort of because of this almost isotropic radiation from the sun. Is it clear, or yeah? If there was no atmosphere, you would actually, the day would be dark if you look away from the sun, and it would be very, very bright if you look at the sun. Okay, so this is about flux. So if you have an isotropic source, of light, for example, the sun, right? Sun is an isotropic source of radiation because it emits in all directions equally, right? So then how does the flux go as a function of distance from that source. So if this is, say, distance r1 and this is some other distance r2, we know that the farther you are from the object, the lesser energy you will intercept per unit area. Right, so by the conservation of it, so we are assuming that the photons are not absorbed on the way. So the flux at radius r1 times the area at radius r1, which is just 4 pi r1 squared, is equal to flux at radius r2 times 4 pi r2 square. Right, this is just this, so flux times the area, this is amount of energy crossing per unit time, this radius r1, this full shell, spherical shell at r1, this is the amount of energy that crosses it per unit time. And we are assuming a steady condition, so these photons are not absorbed on the way. The same photons will cross in the same time that they cross the inner shell. So this is equal to the energy per unit area times the area of this shell. So the flux is proportional to 1 by r squared. I mean, this is very well known, of course. And we know that flux is equal to luminosity divided by 4 pi d squared, right? Where d is the distance to the object. So we can actually calculate how much flux is received at the Earth because of the sun. So solar luminosity, generally when we talk about the sun, we use this symbol. This is the symbol for the sun. So solar luminosity is about 4 times 10 to the 33. What is the unit for this? Anyone?
What?
Erg per second. This is luminosity. Ergs is energy, and energy per unit time. This is luminosity. And what is the value of D? 1 AU is 1.5 times 10 to the 15, 10 to the 13 centimeter. Okay, so if you plug this in, you get the flux that you receive at the location of the Earth. Right, so if you use a bigger telescope or a bigger detector, you have more energy collected per unit time, but the energy per unit area per unit time is constant at the same distance. Right, if you use a bigger detector, you'll have more energy crossing it per unit time. So a better thing to use is per unit area. So that's why flux is more natural than energy per unit time, because the energy per unit time that is received by a detector is proportional to the area of that detector. And of course, if you align your detector perpendicular to the line joining the sun and the Earth, you will get 0, right? Because this is this cos theta factor. Okay. So what I will do is, this is fairly simple stuff till now. What I'll do is I'll introduce this concept of specific intensity. Any question on this, by the way? This is fairly simple. All of you should perhaps know this very, very well. Now let me just mention before I end the class this notion of something called, this is important. This is something that you may not have, specific intensity. So this is the notion that I want to end this class with. So specific intensity. Now here, in the case of the flux, we considered photons traveling in all possible directions, right? So you can have photons going in this direction, that direction, and all possible directions. So flux is not the most fundamental description or fundamental macroscopic description of radiation, right? The quantity that's more fundamental is something called specific intensity, or we denoted by I nu. This is specific intensity. So what is it? So if you consider rays of photons traveling in some given direction, right? And if you consider an area which is perpendicular to that, so consider a small area perpendicular to a given direction in which you are considering photons. So, and you don't consider single ray, you consider a bundle of rays, and this is called group of rays which are within some small solid angle d omega, right? So you all know solid angle, right? So solid angle is equal to the transverse area divided by the distance squared, right? So if you consider a point here, okay, and you have like an area, some area here which is not aligned in this direction, right? But you can always project this, right? So this, if this angle between this area n hat and this omega hat is theta, then this area which is transverse to it is just d. So if this is angle theta, so area perp is nothing but area times the cos theta, right? Where angle theta is the direction between this area normal and the direction of the ray. So dA perp is dA cos theta. So solid angle is nothing but the perpendicular area divided by the distance squared. I mean, this is, all of you should know it. So this is just, this is sort of quantifying how much of the fraction of a shell, like a spherical shell, is some area occupying. Okay, so this is like a small solid angle, and you're considering a surface which is perpendicular to it. So this is like a perpendicular area. So the amount of energy crossing this area per unit time. So this is dE is the amount of energy in photons that's crossing this area dA per unit time. So this is equal to, so this is how we define the specific intensity, I nu. So I nu times dA. So this area is dA. And this is perpendicular. So you are not given an area, you're given a direction of rays, like a small spread in the direction of the rays. And now you consider an area which is perpendicular to it. You consider this area which is perpendicular to it, and so your energy crossing this this area is of course proportional to dA. It's also proportional to d omega. It's proportional to the time for which you are measuring, and it's also proportional to the frequency range that you're looking at. So this is specific intensity. This is the amount of energy crossing perpendicular area per unit solid angle, per unit time, per unit frequency. So the units of energy is of course erg. So the units of I nu or specific intensity is erg per centimeter square per steradian. So the units of solid angle is sort of dimensionless, but it's always good to put this per steradian there because it gives you a sense of what you're measuring. Per second per hertz. You will actually notice that second and hertz are inverse of each other, but you still explicitly write it like this because this has some interpretation, right? I nu has the dimensions of this. So this is the energy per unit area, per unit solid angle, per unit time, per unit frequency. Okay, so this is the most fundamental way of quantifying radiation, right? The flux that we talked about here, we are considering all possible directions. So if we add up the specific intensities in a particular way and integrate over all possible directions, we get the flux. So flux is not as fundamental. This is much more fundamental in the sense of this is the most basic description of photons. So, you know, for example, if you're given some position in space and if you're asked, how do you describe the radiation field in a macroscopic way? The most basic thing that you can tell is how much energy is going in all possible directions. So how much energy is going in this direction per unit time, per unit area, in this frequency range nu to nu plus d nu, right? So this is the most, you know, this is basically the most detailed macroscopic variable that you can use to describe radiation. So this is called specific intensity. And the important thing to notice here is this is the area which is you are choosing an area which is perpendicular to the given direction of photons. Okay. Now, if you are given like a general area, if you're so, you know, is this clear? Specific intensity. Hello. Yeah. So. Right. So if you're sort of, if you're asked, so suppose you're given an area which is not necessarily along the direction of the ray that you're considering. So this is the area normal n hat. And if you're considering rays in some other direction, say omega hat, right? In this case, there is an angle theta between these two directions. And in this case, how much will be the energy? Right, so since dA perp is dA cos theta, so dE in this case would be so this is the energy going in that particular direction at that particular frequency range in particular time dt, right? So this times dA cos theta times d omega dt d nu. Right, so don't forget this cos theta is very, very important. Right, this is the energy specific. dE is the energy crossing this area, and if the area is not aligned perpendicular to the ray, you will have this cos theta factor. So this is the energy crossing this area. You can also talk about the number of photons crossing this area per unit time, per unit frequency. And that's just dE by h nu, right? Because we know that every photon carries an energy h nu, and the frequency nu is fixed. So this is the number of photons crossing this area in time delta t in frequency range nu to nu plus d nu along the solid angle omega to omega plus d omega. Okay, so you know this I knew is actually a function of position, space, function of direction, frequency, and time, right? So this is actually like, you know, some of you may have done fluid mechanics, right? We have things like pressure, velocity field, density. They are only functions of space and time. Here you have these three additional variables, two directions, right? So if you have two direction variables and one energy variable, right? So any direction can be specified by two variables, right? Like theta and phi. If you choose spherical coordinates, all you have to tell is what is theta and what is phi coordinate, and you know the direction in which you're pointing. So these are the two angular direction, and this is the energy direction or the frequency direction. Does this remind you of something else? There is something called a distribution function that we are used to, like when you do statistical mechanics. Distribution function is a function of space, momentum, and time, right? So generally we like to talk about, you know, these three variables and these are actually equivalent. And I knew is very, you know, in fact this guy or I knew by h nu. This is really related to I knew by h nu. This is the number, right? This is related to the number of photons. This is the distribution function. How many particles, right? This is how many particles are there in the volume d3x, d3p, right? So there is a very close connection between the specific intensity and the phase space distribution function, or mu space distribution function, right? So this is not the 6 n-dimensional distribution function. This is an n-dimensional, this is a 3D, 3 plus 3, 6-dimensional phase space. This is sometimes called mu space. Okay, and this is what we deal with in the Boltzmann equation, for example. So I'm actually done with the material today, but I think this concept is a slightly, this is just sort of counting in a sense, but there are some subtleties involved. So you start reading the book, okay? And are there any questions? This mu space, has anyone heard about mu space, or do you have an idea of what I'm talking about here when I say distribution function? Can someone respond, please? No? Cannot hear you.
Is it like a phase space density function means?
Yes, this is exactly the phase space density function, right? So, normally if you have n particles, you take into, you have the 6 n-dimensional space. That is not this. We don't want that detailed description. What we have is a phase space density, or a distribution function, which is in 6-dimensional space. And all we care about is how many photons there are at this position and at this momentum. And a more convenient variable than the photon momentum is their directions and their energies, right? We know that momentum of a photon is nothing but energy divided by the speed of light. So these are actually 1-to-1, right? This P and those two are actually the same, right? So P is equal to H mu by C in the direction of, this n hat, I should call it omega hat, because n hat I'm using for the area normal. Don't confuse. So I'm using n hat for area normal and omega hat for the direction of the photon. This is really omega hat. So this is the relation between the momentum of the photon and the direction of the photon and the energy of the photon. Okay, so I think I'm done for today's class. So this material actually you can access on this. So let me go back to the. So this is on the general channel in class notebook. If you go to general class notebook, and if you click on content library, this is where I have this. So you can actually look at my scribblings there. I think you can sort of change right, the size and so on, so you can actually move along. So just let me know. So just last 2-3 minutes I want to spend on is this okay, or should I try using a blackboard?
It's actually nice.
This is okay?
Yes, sir.
So today this pad was not working actually, so I will have to figure this out. So I was using my mouse, which actually turned out not to be all that bad. So this material will be at the same place. So I will not write a lot of things. I will just use illustrations, but I'll speak a lot. So there's still this class is anyway being recorded. Okay, so you will have access to all the material, but make the class more interactive. Stop me, ask me questions. That way things will be more clear, because material wise all this is available. You have the book. Okay, so are you all able to access the book is here in the files in the general portion. Class material books are here. And on the class channel, we will have these notes is where you will have this material and recordings. Could you access the recordings on stream? Some of you?
No, sir. Yeah, I was able to access it.
Oh, wow. What happened to this?
Yeah, actually, I added notes for today's class after you.
Okay. Okay. Sorry. So this is actually here in the class notebook, in the general page. This is more customized for a class setup. What we saw was slightly different. So this is where it is, content library. So this is where the material is, and I'm actually just going to write one after another, so it's at one single place. Anyway, I'm also very new to all this, so I will also.
Sir, I think only the IISc students can access the streams. The rest of us can't.
But actually, okay, let's go to that issue. So no more questions on the class material, right? Please read the book, sections 1.1, 1.2, 1.3. This is the material till 1.3. Okay. So let's go to that issue. So I sort of sent this link. If I click on that, it takes me to the stream, and there is this recording from lecture 1. I can easily access it, and if I look at, see, this is shared with view settings. It's my content channels. So this is the channel.
Sir, the stream itself is a paid subscription. So, I mean, only IISc students has free access to it. The rest of the RRI students, I mean, as for RRI, we don't have access.
Oh, is that true?
You might have to change some settings.
But see, just I thought this was like a because I could actually see the people who are there on Teams are also people who I am sharing this with. Just as X channel. So this is the channel who are the members of this. So here I see all the people, right? There are also IIAP and Gmail and so on. So these are all members of this channel. So I thought that the members would be able to access.
I will try again and
so try it, because I've actually added you to the channel, and if I go to the videos, this is in that channel. So I think you should be able to access it. Try it and let me know. Okay, because you are
process it was working for guests.
You are there in the channel. So is there anyone who's from not from IISc using some external email ID and is able to view it? No.
Sir,
Anyway, yes.
I'm an IA student. I'm also having the same problem.
So you're not able to see the recording.
It's like he said that it might be due to because it is only registered for IISc students.
No, but that's also true about Teams. I was able to do the.
No, sir. Like Teams is not paid. I mean, Stream is a paid subscription.
Okay. So we will have to do something else.
Teams you can use for you can create personal accounts, but in Streams you can't. But I will still try again once today.
I think you can upload the recordings in Teams itself, like in the file section, just as a recording.
Yeah, that will be better, sir.
Yeah.
Because we can download it and then.
I mean, that's already, isn't that here?
That's already there also.
It is already there, right? If you go to these recordings stay for like 20 days or something, that's what I saw. So the recordings are already there. But I think what Stream does is it's sort of like watching YouTube. If your connection is not good, it will degrade the resolution and you can watch it still. Let me figure it out. I'll just put it on YouTube, forget about You forget about all this then. Let's see. Let me know. You try other things and Google a little bit. If it doesn't work, then I will just put it on YouTube. Okay, that is
I have
accessible.
a question about class timings. Is it 1.5 hours or 1 hour?
It's actually 1 hour. I'm sorry, that I have exceeded, but there have been interruptions. It's 1 hour. Although I do 1 hour 15 minutes because uh, this format is a little difficult and we are still getting used to it. So there is no class after this, right? But you still have to have lunch. I'm sorry about that. Hopefully, I will try not to exceed by more than 10 minutes. Okay. Anything else? No. So okay.
Sir, one thing else. You said there will be 4 exams, right?
Yes.
So we will know beforehand, right? That when the exams will be, or will it be like surprise?
No. It will not be surprise. They will be mostly at the end of October, end of November, end of December, and middle of January. That's when the semester ends.
Okay. Thanks.
Okay. So they will not be surprise tests. You will know about them beforehand. Okay, and lot of most of the questions there will be from homework, so you should do homeworks. Okay, if there are no more questions, I'll end the session. Okay, bye. Take care.
Thank you, sir.
Mhm.